So I'm going to use the limit definition here, and then I will find the derivative specifically at the point 6,3. I'm going to write out that limit definition with h this time. Most of you are probably going to prefer it with an h anyway. But just so that you could see it different ways, it's not bad that you saw it with the delta x. So what I'm going to do is I'm going to, and this time I guess the function's not named f, it's named b. But I'm just going to go ahead and rewrite this limit and customize it specifically for the expression for this function. So where it says x, I'm going to replace x with the input x plus h. So this would be the square root of x plus h plus 3. And then minus, and I need to be subtracting off from this the original function where x is the input. And this is all over h. Now if I try to substitute in right now, I'm going to get 0 over 0, which is an indeterminate form. So I need to try to simplify this. Well, our strategy when we're dealing with these radical expressions is to multiply by the conjugate of the numerator, because we're going to rationalize the numerator. And so I'm going to multiply by the conjugate of the numerator on both the numerator and the denominator. I'm going to go through the multiplication rapidly here, and if you need more help with that, please schedule time with one of your teachers or with Earl. All right, so on the numerator, if I FOIL this out, I would end up with x plus h plus 3. Middle terms are going to cancel out, and then I'd have minus the expression x plus 3. I'm going to have to distribute that negative. On the denominator, I'm not going to distribute on the denominator. That's a strategy that is a good one in general when you are dealing with rationalizing the numerator. Well, if I simplify my numerator just a little bit more by distributing the negative and then, pardon me, canceling out terms, I would end up with, on the numerator, simply h. And on the denominator, I also have h as a factor. And so a factor on the numerator that repeats as a factor on the denominator can be reduced out. So I'm going to divide both of these by h, leaving just a 1. And now I'm going to substitute in a 0. So I'm not writing the limit notation any further because I'm putting in a 0 for h. So I'm not going to write that h anymore. And so what I have found out, if I simplify this expression, let's see, this original equation was called b, is that the derivative, b prime of x, is equal to 1 over, and I had like terms on the denominator, so I'm going to combine them 1 over 2 times the square root of x plus 3. That's the actual expression for the derivative. I also, and by the way, there's no need to rationalize. I also now want to find this derivative specifically at the ordered pair 6, 3. So I'm now going to take this expression and substitute in a 6 for x. So that would become the square root of 9, which is 3, and I would end up with 1/6 as the slope. Let me give you a quick visual connect on what's happening with this problem. This is the square root of x plus 3, which looks something like this. At the ordered pair 6, 3, the slope of the tangent line here is 1 over 6, up 1 and over 6. Not drawn a scale. All right, for example 4, why don't you take a minute and try this on your own. You can turn off or pause the video and then turn it back on when you think you're ready. And I'm going to go through these. So for those of you who are ready now, I'm going to go through this one. So there are a couple different forms for a derivative. And so I want to check and see if they match the form. So first there's the limit form with h. And the limit form with h should be the limit as h approaches 0 of this function with an input of x plus h minus this same original function over h. And because we are subtracting a negative, this would become a plus, which is a match for part A. For part B, you may not recognize this one. This one is in the form the limit as x approaches some constant a of f of x minus f of a over x minus a. Well, in this particular problem, a is the constant 2. So let me see if I can rewrite this specifically for this function. So I have f of x, which is the expression negative 2x, minus f of 2. This would then be f of 2. Well, if I substitute in a 2 here into the equation, I would end up with negative 2 times 2, or negative 4, which ends up being plus 4, over x minus the input that I'm using as my constant, which is 2. This is another match. If I examine part C, if I look at the original equation, this is a line. And since this is a line, the derivative is the slope of this line, which in this case is negative 2. Now D is actually very close to A, but what happened in D is they didn't miss the sign change because of subtracting a negative. So D is not correct. When we talk about rates of change, you're going to hear people reference average rate of change, and you're going to hear people reference instantaneous rates of change. An average rate of change is the rate of change over an interval, where we have a starting and a stopping point that are two different points. It is the slope of the secant line. The slope of the secant line. It is the slope of line connecting the endpoints of the secant. Let's see, maybe my pen might be working. And so minus a. That is called the average over the f of endpoint is pair a comma f of a, and the second ordered pair is b comma f of b, and then this is just a slope formula. However, if you are hearing someone reference an instantaneous rate of change, an instantaneous rate of change is the derivative evaluated at one point A, which is the slope of the tangent line, which is our limit. This is one of the two limit definition forms from the previous page. And we kind of looked at that a little bit up here as well. So average rate of change is over 2 points. It's just your regular slope formula, versus instantaneous rate of change is your